at least in part, naturally induced. This is a long debate, and therefore the result is that people that did this figure, which is in the public domain, they placed climate change in both categories, natural drivers and human drivers. Okay, I think I did everything here. I mentioned everything here, and let's now see this other figure. So you see here they use, these are human-induced drivers. They use the term exacerbated climate change to imply that it's human-induced in this case. I think it is a reasonable way to present it. Land use change, river modification because river training usually limits the interaction between surface water and groundwater. If you train a river, you reduce replenishment of groundwater bodies from the river. Land use change reduces infiltration. Urbanization, we urbanize areas along the coasts, we reduce infiltration, saltwater comes in. Groundwater abstraction, accelerated subsidence, human-induced, because, as I said, if you pump oil and gases, if you pump water. Land drainage. Land drainage is something that we try to organize to be very efficient. We want to drain the land, because otherwise, when it rains, you know, we may get not flooded, but we may get some water disturbing our activities. So we try to drain the land, like with urban sewer systems. We don't want water running along the roads, and therefore we collect water in sewer systems. The problem is that infiltration is reduced. Even if you drain agricultural areas, and you want to drain them because you don't want the soil to be rushed away, to be taken away from flowing water, but in doing that we reduce infiltration.
Excuse me. The vertical axis shows the area affected by this.
Yeah, more or less. And I see a bit of inconsistency here, because I think they should write here global scale, not regional. It's reasonable that they start from a very small spatial scale, but I think climate change may be regional, but it's, I think this should be made longer, this vertical axis, and include global scale. Okay, good. These are the drivers. And here you see a schematic representation in the picture on how humans tend to transform the coastal environment. It's self-explaining. Usually we try to organize the coastal environment because we want that the coastline is very well defined. If it's not very well defined, it means that it's difficult for humans to benefit from tourism, for instance. Because you may have marshes in the coastal areas. You may have coastal areas that are not healthy for humans. So we try to define it along a well-structured line, but in doing that, we limit the diversity of the ecosystem, and we limit the possibility to capture fresh water through infiltration, and therefore balancing saltwater intrusion. And also we tend to dig wells in order to take fresh water. And you see here what is the result. And this is a river from which we try to limit the infiltration. So basically you have in light blue the fresh water, in dark blue the salt water, and you see this intrusion. They have the shape, the saltwater intrusion has always the shape of a wedge, okay, cuneo in Italian, because of this interaction between the two flows. And you see here the wedges are of limited extension. Here we have the wedges expanding. And here the situation also depicts a rocky layer which may divide a phreatic aquifer, which is in contact with the atmosphere through the porous media, the porous soil, and a confined aquifer. Confined aquifer is not a direct contact with the atmosphere, but you may have intrusion in both confined and unconfined aquifers. The unconfined is also called phreatic, the confined is also called artesian. So this picture clarifies how we develop the environment, and we may favor saltwater intrusion in doing that. Here you see a sketch that is handmade by me. So basically you have what I already depicted, infiltration, and you have also rivers that may feed with fresh water groundwater bodies, and then you have the interaction between the salt water and fresh water, and if salt water intrudes, it may reach the roots of the trees, and the trees may die from this. Okay. Now, the problem is a bit technical, so let me show you. No, it's not a figure, but I write on the blackboard. So we have to, as I said, the problem is a bit technical. We have to study how water flows in the underground. And there is a law, a physical law, describing groundwater flow. It's Darcy's law. Let's try to understand it. It's Darcy's law. Which is just a kind of energy balance equation. Okay? It's just an energy balance equation that is developed under certain assumptions. And let me write it as it's written here. Q is equal to K A J equal to K A derivative of H with respect to X. Okay, this is Darcy's law. Let's try to understand it. First of all, this law was derived empirically by Henry Darcy. He wanted to study how water flows through a porous medium. So what he did was, in the lab, he made a device that allowed him to flow water through sand. And what he did was precisely to build a device like this. There is let me think on how I can draw it. So there was a pipe that was filled by sand. This is sand. And here we have a filter. And here we have a filter. And then the pipe continues. And here we have a tank with water. This is a tank with water. On the other side, the pipe continues. And here we have another tank with water. Okay? And in static conditions, first of all, the filter has only the purpose of keeping the sand in a limited portion of the pipe. And in static conditions, you expect that the water level in the two tanks is the same. for the principles of the communicating pipes. Okay? Principi dei vasi comunicanti in teglia. You expect in static condition that you get water at the same level. Keep in mind that water can flow through the sand. What he did was, with a small pump, he started lowering the level of water into the second tank. So he put the water level here. And he lowered the water level again by pumping with a small pump. And of course, if you create a difference in water level, a flow of water originates through the pipe and through the sand. He observed that if he fixed the pump at a constant rate, the water level in the second tank lowered and then reached a steady state situation. And then he tried to accelerate the pump, and then by increasing the flow that is removed from here, he noticed that the difference in level increased between the two tanks and then reached another steady state situation. So the higher the flow, the higher the difference in level between the two tanks. Let's call it delta H. So he verified that he could derive an analytical relationship in the form flow is equal to a constant times delta H. And he realized that the longer the body of sand, the lower the flow. Of course. So he refined the empirical relationship by saying that by dividing delta H by, let's say by L. What is L? L is this. Do you already know about Darcy's law? Just you and you. Okay, and you. Okay. And then he also realized that, because you know, ideally, when you determine an empirical relationship, you find that there is a constant that you need to introduce that takes into account the empirical drivers, the things that you don't understand. Ideally, you are already happy when you realize that K is a constant, which means that it doesn't depend on the flow, it doesn't depend on other behaviors that you can physically understand, explain, based on your understanding of the physics. But on the other hand, we are a bit unhappy that we don't understand what determines the constant, what determines K. So Darcy, what he did, he tried to explain part of K with physical reasoning. So he understood that, for instance, by dividing delta H by L, he could, at least in part, explain the constant with the physical parameters, the length of sand. This was the first achievement. A second achievement was that he understood that he could introduce here another multiplier, which is the area of the pipe. Because, of course, the larger the pipe, the larger the flow. So, this was another piece of understanding that is introduced. And therefore, he could conclude that at this stage, K only depends on the media. This was the stage at which he got. K depends on the media, on the sand. If we have higher permeability, the higher the K. And what is the dimension of K? If we make a dimensional analysis here, we have that Q is a flow. What is the dimension of Q? First of all, let's say that we can write that the dimension of Q should be equal to the dimension of K times the dimension of delta H divided by the dimension of delta L, times the dimension of A. Okay, this is dimensional analysis. How do we measure flow? Dimension of flow is volume per unit time. This is how we define water flow. Volume of water per unit time that passes through a whatever medium, a pipe, for instance. Okay, dimension of K, we don't know it. So, dimension of delta H is L, dimension of L is L, dimension of A is L squared. And therefore we derive that dimension of K is equal to L divided by time times L squared. Just 1 second. Divided by L squared. And there is something that is not correct.
It's
The first one is L
is big. Correct? Let me see. Okay, is yeah, correct. Just 1 second. Okay, T divided by L, correct? No, it's
The discharge
Q is
is common to
L
3.
cubic divided by
It's the volume.
okay. It's a volume. Okay. So yeah, correct. Now it's correct. It's a velocity. Okay, it's a velocity. It's called hydraulic permeability. In Italian it's called conducività idraulica or permeabilità idraulica. Hydraulic permeability. Okay, good. This is what he understood, and basically this is what you see written here, which was derived by web page. And what can you see here, basically? The same relationship, because it's delta H divided by L can be written in differential form in the partial derivative of H with respect to X, where X is the abscissa along the direction of the flow. Good. So, what is the interpretation, the physical interpretation of this relationship? Basically, the flow is given by the area of the pipe, which is fine. And if you refer to a porous media, it's the area of the porous media. I will give you more details later. And here we have the derivative of the difference in elevation of water level in the two tanks with respect to the length of the path through the porous media. What is the meaning of difference in elevation? In static conditions, it's a difference in energy. It's a difference in potential energy. And if we assume that the flow here is very, very slow, like it is in a porous media, we can assume that kinetic energy is negligible. And therefore, basically, energy is given by the potential energy. So, delta H, dH, is energy spent by water to flow through the porous media. So the derivative of energy. We introduced here a fundamental assumption of groundwater flow, that the motion is very slow. Just 1 second. So the motion is very slow. And this assumption justifies the fact that the flow is linearly proportional to the difference in energy. Because otherwise, if the flow was not slow, we know that the flow is proportional to the square of the difference of the energy. Sorry, it's the opposite. The opposite. The energy losses are proportional to the square of the velocity. And therefore, the flow, the energy losses are proportional to the square of the flow. Okay, so let's say, let's not make it too complicated. Let's say that the linear relationship is only valid if the motion is very slow. Okay, because it means that energy losses are directly proportional to flow. With faster flow, the energy losses are proportional to the square of the flow. Okay, and there is one more thing that we have to say. Darcy made implicitly another assumption. He made the assumption that the flow was monodimensional. I want to be clear. Here, the motion of the flow is taking place mainly in one direction. You know that motion can take place in 3 directions in general. When you have a dominant direction of motion, you are allowed to make the 1D assumption. You are allowed to assume that the flow is monodimensional. It means that water goes just along one direction. In the other 2 directions, it doesn't go. This is an implicit assumption that he made. But actually, Darcy's law is only valid in the 1D direction. And therefore, we can better specify the meaning of A. What is A? It's the area of flow. And it's clearly specified what is the direction of this area. It's the area along the other 2 directions of space, but the direction of flow. So let's suppose that you have a pipe like this. I have flow along this direction clearly. And let's suppose that I cut the pipe with a plane that is perpendicular to the direction of flow. And let me depict it. This is my pipe, and this is A. If the area over a plane, the area of the pipe, over a plane that is orthogonal to flow direction. So I have water coming out from the blackboard perpendicularly. This is how the area of flow is defined. Now, if we want to refer to an aquifer, we have to make this same assumption. Flow is slow, first assumption. Second assumption, flow is 1D. So there is a dominant direction of flow, which is fine because flow from the land to the ocean is taking place mainly in one direction. And therefore, if we want to estimate A for an aquifer, we have to cut the aquifer with a plane that is perpendicular, orthogonal, to the direction of flow. So this is Darcy's law. It is important that we remember the slow. I may ask you at the exam. I will also propose to do a self-assessment test in which I will ask. I hope by next week I will present you on the IOL website a self-assessment test. I will describe you later how it works. And I will ask you some questions about Darcy's law. I may ask you at the exam to write down Darcy's law and the assumptions under which it's valid. Actually, we will study saltwater intrusion in a completely static environment, so we don't really need to know, to apply for our purposes, for our first treatment of the subject, we don't really need to apply Darcy's law. You will see, we will refer to a static picture. But actually, a real-world situation, if you want to understand how the water table behaves and how it evolves, you need to apply Darcy's law. Okay, this is just to start. Okay, and one other thing before we move forward, this is basically an illustration of Darcy's experiment. It's a bit different with respect to mine, with respect on the blackboard, but it's the same thing. One other thing that we need to know is the hydrostatic law. So raise your hand if you already know the hydrostatic law. And let me write it down first. Hydrostatic law is written in a way that can be this one. Do you know it already? Yeah, you know it? Maybe. Okay. Okay, let's discuss it. First of all, let's refer to a body of water. And for simplicity, let's refer to a tank. But we may refer also to an aquifer. The only assumption is that the body of water is in static conditions. Water is not flowing. Or, if it is flowing, it's flowing very slowly. Okay? So, a tank is the ideal example. In a tank, water is not moving. Okay? Now, let me refer to a generic fluid particle. A particle is a point in the flow, where we assume that mass is concentrated. It's an infinitesimal mass. Okay? And let's, just 1 second, because I need to be coherent with the symbols there. I hope I am coherent with the symbols I'm using in the web page, but anyway, you don't be concerned by a change of symbols. And let me say that, okay, so let me indicate with Z the elevation of the particle with respect to a reference horizontal plane. Let's suppose that the bottom of the tank is horizontal, and let me take the bottom of the tank as plane of reference plane, whatever. Okay, that's fine. And let me indicate with P the pressure of water on the particle. And we know what is the value of water pressure if we indicate with lowercase h the water depth over the particle. Pressure is equal to gamma times h. And let me indicate with capital H water depth in the tank. Okay, so what does it happen if you move this particle? Of course, if you move the particle up, you have a pressure decreasing. And if you move the particle down, the pressure increases. So let me study the summation of z plus p divided by gamma. What I want to study is the interplay between the position of the particle in terms of moving up and down, as indicated by z, and the pressure. But let me write the pressure how it's written here. So z plus gamma h divided by gamma. So this is z plus h, but this is equal to capital H. And therefore I can conclude precisely what's written here. It's constant. In this case, it's equal to capital H because I assumed as reference plane the bottom of the tank. If I assumed another reference plane, not necessarily Z plus P divided by gamma is equal to H, capital H. We may say that it's constant anyway. This is hydrostatic pressure. It's important because I want to study the position of the interface between salt water and fresh water. And if, by recalling the previous picture, if I consider a particle of water that is sitting on the interface, this particle of water is in equilibrium, and therefore I can locate its position by imposing that the pressure of fresh water, hydrostatic pressure, it's equivalent, it's the same as the pressure of salt water. So for this reason I start from the hydrostatic law. Actually water is moving, but it's moving very slowly. And therefore I can assume that I can work in static conditions. Okay. Yeah? Please. You have a question?
No.
Ah, no, okay. That's fine, sorry. I don't understand why I lost the adjustments. It's looking for the page. Okay, so this is the situation I refer to. So basically, you have the sea, you have the aquifer. Let's assume that you have an impervious layer, a not permeable layer in the bottom. This is not necessarily an assumption that needs to be introduced. It's not necessary, but in order to make the figure clear. And then we have to study this interplay between salt water and fresh water. Of course, you may have flow of water from the sea to the land, or we may have the opposite. And the position of the interface, of course, is governed by the comparison between these two flows. Now, what we have to do is basically to impose the equilibrium of, like I did here, of the particle of fluids, or particles of fluid that are lying, that are sitting over the interface. And with this very simple equilibrium condition, we estimate the position of the interface depending on the seawater level and the level of water in the land, the level of fresh water in the land. I propose that we postpone this to the next lecture. We are almost there. I mean, this is very simple. It's a very simple equilibrium condition. We are almost there, but let's take at least 15 minutes to discuss it. And now I think it's already time to go for lunch. Okay? Okay, that's it. Do you have any question?